Yeah, so it's going to be a graph G, and then you'll select two special vertices in there. And let's say it's these two, this S and this T. They'll be denoted source and sink respectively. Okay, sure, my handwriting is a little worse than what I expected, but sure. And then there will be this capacity function. And then there will be a capacity function over the edges of G. So let's see edges like this. Oh, also, in case I didn't mention, the edges are directed. Yeah. Then each of these has a capacity function, which basically, when we define flows, the capacity function makes sense. The flow values will be restricted by the capacity on the edges. So then we defined a flow as a function on the edges of G, like a function on the network, particularly on the edges, such that it's always between 0 and the capacity function. On which note, the capacity function is it's necessarily non-negative for any edge you pick. So then we just discussed the notation stuff. After that, we discussed what the statement of the maximum min cut theorem is. So we then defined a cut. A cut is a well, you first find any set of edges which if you delete them, let's say, can you change the pen colors? Let's say I delete these three edges here. I just like make a red line to show that I've deleted them. Then I can take the sum of their capacities. Okay, so like if I disconnect S and T, I don't have to just disconnect the graph arbitrarily. I could have disconnected the graph like this, let's say. This still technically disconnects the graph. This vertex is isolated. This is not a cut because S and T are still connected in the other part. So a cut first off disconnects S and T in particular, not just the graph. And the cut has a value. The value of the cut is said to be the sum of the capacities of each of the edges you have deleted. And then we talked about the notion of a value of a flow. So what we did was we defined an f of capital S. This was defined to be the sum of flows across all the edges going from S to neighbors of S, right? So we first defined an f of S, and then we said, no wait, actually we defined an f as SP. So this was summation of the flow of E, where E goes from S to T, like the one the like if F is UV, the edge E is UV. Remember the order matters. Then U is in S and V is in T. We take the sum of all such flows, and this is defined to be FST. So what we said was F of S V. So basically, the sum of flows across these edges is equal to F of S V minus S. Yeah, where S is contained in S. Whenever S is contained in S and T is not contained in S, then we have that f of S V over S is equal to this quantity, and thus we call this quantity the flow value. So once we have defined the cut value and the flow values, the statement of the theorem was uh, max of the flow value is equal to the minimum possible cut value. You guys are following, right? Like just tell me yes or okay or something at times, and like feel free to interrupt me even while I'm not talking. It's not necessary to wait for me to stop or something. Okay. Actually, can you guys first confirm that you can hear me? Like since I started talking. Okay, you can, right? Okay,
Yes,
so just and you guys followed this far, right? Or is there some part which was not elaborate? Okay, if nobody's saying okay, just say yes if you guys understood everything. Fine, I guess I will assume you guys said everything. I ask you guys to respond, you guys don't talk. I can't do much about that. So the maximum value of the flow is supposed to be equal to the minimum value of the cut. This is our theorem. And then we gave a proof for the integral values. So the idea was, the initial idea that we tried out was, you just you have this idea of an augmenting path. It's the path where like you move along the edges. Let's say I'm not drawing the edges, not relevant to the path right now. So what you do is you construct the flow step by step. If at any step you find a path where the flow value is less than C value for every edge on this path from S to T. I'll just use S and T for every source and sink you'll find on any graph, okay? So you take this path and you pass as much flow through this as possible, okay? So eventually what happens is one of the edges is going to approach your maximum capacity and the flow is going to the flow is yeah, so the path gets saturated. On which note, I should remind you guys what saturation means. An edge is said to be saturated if the flow and capacity values get equal. So basically, we are using unsaturated edges and we are trying to find a path through them from S to T. So this increases the flow. And we had discussed one thing earlier. Uh, max flow is less than equal to min cut. We had discussed this earlier. This was relatively much easier than the problem we are dealing with. That is showing that with the right choice of f and c, equality will definitely hold. Okay, so we know that f is increasing. We know that f is bounded. So eventually this algorithm will stop. So we hope that this will give us the maximum flow. But then we didn't really discuss a proof. I mean, we discussed a hand wavy intuitive argument as to why this should work. And the reason we only discussed in hand wavy intuitive argument is this example. By the way, you guys can see the page has changed, right? I just went to the third page.
yeah, it's visible.
Okay, it's visible, right? Okay, so the reason why we did not discuss a proper proof is, let's look at this example. I'll just draw these as big circles. They actually look nicer that way, I think. Hmm. There'll be a minute of silence. I'm just making the graph, not saying anything, okay? Yeah. Okay, so this is our graph. Then I'll first, in blue, I will write the capacity values. This is, let's say, 10. By the way, you guys can see the arrows properly, right? Like it's honestly, it's not very clear. But do you guys see where this goes? I'll just do this again. Hopefully, it's a bit clearer now. So this has capacity 10. This also has capacity 10. This has a capacity 9. This has a capacity 10. And so on. So we do, this can be 4, this can be 6. Actually, I forget about this. I'll direct it this way. I'll direct it upwards. This will be 8. This can again be 10. The 6 a bit close to this, but it's supposed to be this edge here. Now, I'll do exactly as what our algorithm says. I'll pick paths. Um, let's say I pick, yeah, let's say I pick this path here in green. Right now, this is an empty flow, so I can basically pick whatever I want. So here the edges are 10 to 9, 10. And like the remaining capacities are all, they're exactly the full capacities. So here the minimum possible value here is 2. So we'll add a flow of 2 everywhere. So what we'll do is we'll like the flows in green, and then I'll use some other letter for showing the remaining color for the remaining capacity. This is 8. Yeah, okay, this is fine. So this is 2, this is 2, and this is also 2. The capacities which remain are 0, 7, 8. Now what I do is I take this other path and I'll just draw it outside because drawing it directly into the vertices is getting clumsy. So now your maximum remaining capacity here is 7, right? So I can add a flow of 7. 7. This this reaches 9. This reaches. This also reaches 9. And well, the remaining capacities for this is 0. This is 3. This is what's the main capacity? It's 1. Yes, it's 1. The total flow is 9. So, um, so yeah, cool. Now we can make a third one, which goes from here to here. So again, the maximum remaining capacity here would be 4, right? So we add a 4 everywhere. 4, this is 2, so we make it a 6. This becomes a 4. Now we are out of paths, right? We do not have more paths. Uh, okay, no, wait, there's just one more left. Right, right. Give me a second. Mm, yeah, okay. So one last path would be this, right? Now we pass a flow of 4 through this because 4 is all that remains here. Here, wait, you can only pass 1 through this, right? Wait, actually, can you give me a minute? I think I've messed up the counter example and wasted like 5 minutes for you guys. I'm really sorry, but I think I might have messed it up a bit. I'll just tell you what I was doing first. So the thing is, I had a counter example for the claim. The reason we didn't have a proof is the algorithm doesn't work, basically. And I was showing you a counter example. I had it somewhere. Just give me a second, okay? Ah, shoot, I'll have to. It's okay, this looks right. This should be 7, this should be 8. Yes, this is the first path I had to choose. Yeah, okay, next. Let's go for this path. Okay, here's the second path I want to choose. Also, once again, guys, I'm really sorry for the confusion. Please interrupt me if you can anytime. I mean, you guys really don't talk. I don't know if you guys are following or not. It's okay if you guys don't want to talk. Can you at least message me or something? Hello? You know what? I'll generally take time. I'm going to wait 2 full minutes before you guys respond. I have no idea what you guys are. Well, if you guys really don't want to talk, then fine, I guess. At least message or something. I really don't know if the class is following and I could be messing it up real bad. Here's the second path. You go to this vertex, this one. Maybe I should have numbered the vertices. It would have helped a lot. I will number the vertices right now. We'll number them in red. One, two, three. Is that too unreadable? Two, three, four, five, and six. So the first path was one, two, three, four, six. Then our current path, which we are analyzing, is one, two, four, six. Okay, so this gave us a flow value of 2, right? This gave us a flow value of 2. And this is now, we'll check how much flow value this gives. So you have 8 here at the 4 to 6 edge, you have capacity 8 here at the 2 to 4 edge, and for the 1 to 2 edge. So this gives us a capacity of 8. So now our new capacities, residual capacity, this is not 8 anymore, this is 0, this is 0, this is also 0. Good. Yes, okay, I think we're, this is actually a working count example. I'm really sorry for the time that got wasted. I'm really, really sorry. Now we just need to add a third path. The third part goes this way. It goes from 1 to 3, 3 to 4, 4 to 5, 5 to 6, 1, 3, 4, 5, 6. So this, let's look at the residual capacities we have here. It's 10, it's 7, and in this path it's 6, and here it's 10. So you can add a 6 here. Like that's the least part. That's the least value. The remaining capacity is there. So you get a total sum of flow of 16. You can check now that I should just remove everything here. Can I? Okay, these paths like they're not important right now. I think you see the three paths. I'll just write the remaining capacities afterwards. This was 0, right? Oh no, wait, I don't need to actually just take a look at this. It's going to get more complicated otherwise. Look at this thing and make sure to yourself that there are no other paths which you can take. This edge is completely blocked off. This edge is completely blocked off. This edge is completely blocked off. And this edge is also completely blocked off. Wait, is this one? Yes, this one is also completely blocked off. Yes. So the only way you have is from 2, 5, 6, but you can only go from 1 to 3. So there is no other path, and this is the value you get 16. But you can actually find a flow of 19 here. The thing is, this whole process took a lot of time, so I'll have to skip that part. But later you can find a flow with value 19, and 19 is the maximum. So our algorithm is not giving us a maximum value. So one way in which we can optimize this is, see, always increase the flow through every single vertex, right? But like there can be occasions where you can kind of add a flow, but you have to go in a direction reverse of the arrow. You can do that. I'll make one right now. There's two limited colors here actually, now that I think of it. I'll just use red now. I'll show you. So this is going to be, if I go from 1, 3, 2, 5, 6. This is a reverse direction here. So 1, 3, 2, 5, 6. If I go this way, I'm decreasing flow along this edge here. But my net flow is still increasing. The whole thing is still a network. And from here we reach 18. We added a flow of 2 here, right? So the thing is, we want to be able to go backwards on some edges and still somehow manage to have something which is a flow. You can't make this value negative, right? Because flows are also non-negative. So we'll make a small change which makes it doable for naturals. Like after this change, you really are done for the natural number case. If time permits, we'll discuss why it's a bit weird for the real number case. Yeah, we should have time for that. So now what I'm saying is the thing you do, you make a new network for every edge you had earlier. You make a forward edge, you make a backward edge. Every edge you have, forward and backward. Yeah, I'll just skip this process, it's taking a lot of time. So you have two of these, and now what you do is, so here the capacities they will update them according to like as your algorithm proceeds. We will update these values here. Now what we'll do is, suppose you chose this path. Yeah, how can you choose a path? That's the question. You choose paths over this now. The capacities work as follows. Let's say this has capacity, a total capacity of CE, right? So at any stage, the forward vertex will have FE capacity. The backward, see the forward edge, right? And the backward edge will have a capacity of CE minus FE. Is that good? Oh, wait, was it the other way around? Yeah, sorry, it's the other way around. The backward edge has a capacity of FE. The forward edge has a capacity of CE minus FE. So what does this do? Now the thing is, you have that restriction that you can't exceed the capacities, but you can still technically go backwards. You have added this backward edge, and even if you take the full capacity of FE here, you have reversed this, you've gone to zero, but that's not an issue anymore. And what happens when you go backward here? You have chosen this edge, but you're just going in the backward direction here. That's all. Okay. Now what you do is, in this new network, which is called the residual network, residual because the CE minus FE, this is essentially telling you the residual capacity or remaining capacity. What more can you pass through this? So this thing is called a residual network. Here you keep doing the same thing. And now I'll spoil this. This definitely works. This works 100%. So we first discuss why this works. And actually we've discussed why this doesn't. Like, okay, sure, we can see why we could improve technically, but what issue was here which we have managed to solve here? So the thing is, okay, I'm really not sure how much time we'll get, but I'll just give you a rough idea. You just check the expression f of s, we complement s here. Okay, so what you do is you remove the edges which are saturated. We discussed what saturated is, and by removing them, you will get a set of vertices. You'll get a set of vertices which you can reach from our source S here. Reach as in you are not using the vertices which are saturated, so some stuff can get disconnected. You might not reach it. That set is S. You look at f of S, V over S. This quantity may or may not be maximized here. Like if you try to prove that it should be the case, you'll fail. Here the quantity Fs V over S will be maximized. Like let me try to explain this. Why? Like the backward arrow here will help basically. That's the thing. Or no, I should move ahead. Like even if I can't cover it in detail, what you can do is we can discuss it over Discord, the specifics. I need to just tell you the ideas now. So the thing is, this works for naturals. We didn't discuss why this works specifically for naturals, right? So the thing is, as you add the paths, the value is always increasing by at least one. These are natural numbers. So what happens is, as you're increasing the flow constantly, and you know that it's bounded, it's a natural number which is bounded, and you're always increasing it and keeping it natural. You can't increase it forever. Let's say your value is a, it increase, and an upper bound is b. Each time you increase it, it increases by at most one. So you can do it only up to b minus a times at most. Like maybe you're increasing it by more than one, but you're increasing it by at least one. So you have that bound. So Eventually, you stop finding these paths and the process ends. And all your deduction is based off the idea that the process ends. Like what happens when the process ended? You do not have any path going from here to here, even with the residual capacities, right? Let's say if this were my S, I don't think this is going to be the S, but let's say it was. Then I know there's a path from here to here. Sometimes there may not be a path from here to here in your normal graph. The path could be this way. But since you've used the residual network, there is also a path from here to here, right? So, yeah, where was I? Uh, yeah, so the flow keeps increasing like this, and eventually at a point it must stop. With real numbers, that can go a bit bonkers. What can happen is the values could go up, say, at a rate like 2, then it's 2 half, there's 2 3 by 4, and so on. And let's say it could be approaching 3. This could be like, if just it goes up by 1 by 4, it goes up by 1 by 8, and it's a geometric progression, the value that gets added, and this approaches 3. Then maybe you could think, okay, maybe it is approaching the maximum flow value here, right? It's at least approaching it. So maybe you could show that the limit is the limit is the maximum possible flow value. Maybe we could show that, right? Now the thing is that does not happen either. It will approach some value. Sure, it will approach some value. I'm saying that the value it approaches may not be the maximum flow value either. For that, I'll share you the PDF. Like I was planning to give you guys lecture notes. So basically, I would have shared them already, but I haven't completed them. They're nearly complete, but a little bit is remaining. So give me a second. Hmm. Okay, nice. Yeah, just give me a second. I'm trying to share the PDF basically. I think the PDF should be visible now. Yeah. So here I have made the counter example where, yeah, this thing is the counter example. Here we will select we'll select flows in a fashion where your algorithm will never terminate. We will calculate the value of the final flow we get, and then we'll see that it's obviously not the best possible. And thus we'll see that our final algorithm does not work if the values are real numbers. So first let's discuss how the graph is. The S is the source and T is the sink as usual. There are some other verses. Let me zoom in so that you can see it properly. It's a little bit clumsy, I think, the drawing. It's much better than whatever I was doing on the whiteboard though. So these red ones have different weights. Basically xi to yi, where the I are same, like x1 to y1, x2 to y2. These are for special edges. And then the other edges are s to xi. And then you have edges from all xi to yj. Then you have edges from yi to t. And there's this extra edge of y2 to y1. We will talk about later. So the black edges together have a single weight, and the red edges have some weird weights. We will talk about it. So we first make a sequence ai equals this constant to the power n. It meets this recurrence relation an plus 2 equals an minus an plus 1. Okay, so what we are doing in practice is while making this counter example, this construction was done first and we got this reconciliation and then we decide from the relation we got this weird value here. You might be familiar with linear recurrences, I think. And I mean, in particular, this one, this strongly resembles the Fibonacci series for a very good reason. Like in particular, I think if you take a minus and it is the Fibonacci relation. So, and now we take the sum of ai from 0 to infinity, that is b. It's this value, root 5 plus 1 by 2. The exact value doesn't matter. We really don't care. So the black edges, they all have weight b. The red edges, they don't all have the same weight. The x1 to y1 edge has weight a naught, which is 1. The x2 to y2 edge has weight root 5 minus 1 by 2. Now x3 to y3, x4 to y4, they have the same weight. Okay, they have the same weight. They both are a2, which is root 5 minus 1 by 2 squared. So our first path is s x1 y1 t. It's just this path. I can't draw over this. Shoot, it's fine. So s x1 y1 t is our first path. So let's see how much value of flow we can pass through this. It's going to be b a naught b. B is sum of a, like a naught plus a1 plus a2 plus everything, right? So that's necessarily larger than a naught. The flow you can pass through this is a naught. Now what we are going to do is we have two path choices defined here. There's one this and there's another this. What we'll do is we'll repeatedly apply them as long as we can. So the step one is this. So you go from s to x2, x2 to y2, then you go back y2 to x3. Wait, you go back, right? Yeah, x3 to y3, y3 to t. Yeah, right. Wait, I think I have messed up the counter example a bit again. I'm really sorry, just give me a minute. The diagram might be a little bit messed up. Okay, cool, it's fine. If I just change the direction y to x here, if I just alter this edge, the direction, the counter example, it still works fine. Like just that single edge. Then you can choose this path. What's the capacities? Let's check. This is B, this is A2, this is A1, this is B, this is A2, and this is B again. So you can pass A2 through this. Let's look at the change which happens. The change which happens is like we don't care about the BI really. Like don't care about the B. Let's just say that whatever flows we are going to pass, the B will never be a restriction. It's the AI which will be the restriction. That's why I've chosen the B values to be some 1 to infinity here, basically. That's the reason. So uh, you decrease it by A2. So this decreases by A2. So A1 becomes A1 minus A2, which by our recurrence here is A3. So this value is now A3. This is 0. Now you pick the second path. This is considerably more convoluted than the first one. Yes, it is. Now, okay, let's just focus on the red edges, basically xi to yi. The other edges, bi edges, just take my word for it. We are going to be okay with that. X2 to y2, y1 to x1, and x3 to y3. Here, I'll remind you guys, this backward flow is not an issue because we already did x1 y1 t. So there's a flow of a naught through it. You can go back. Okay. Now Uh, so what happens to x to y2? Okay, we'll first check the maximum values available to us, right? So this is A3, it's A1 minus A3, the remaining capacity through this. Then the other edge is y1 to x1. We are not going to be concerned about this either. The flow through this is A naught, and as you'll see, the flows which we'll add now, they will always be a value small enough. We'll check that. Okay, so then you have, yeah, then you have y3 to x3, right? Now you have a flow of A3 through this in the reverse direction, right? Yeah, it's in the reverse direction. So remember that in the first step, we added the flow here. So it's the plus A2 minus A3. This will become A4 later. It should, right? Just give me a second. Mm, yeah, okay. So this actually becomes A3. This becomes A3, and you keep repeating this. And you'll check that at step n. At step n, you'll be adding a value of mm, an plus 1 here, and here you'll be adding an plus 2. And every time you do this, these paths will always be augmenting paths. None of these edges will saturate. You'll have to check that, but we have completely run out of time for doing that. So just take my word for it. So at each step, starting from step one, you like I should call them iteration one. I'm already calling these steps. So in the first iteration, this is giving you A2, this is giving you A3. Second iteration, this is giving you A3, this is giving you A4. And in the beginning, we had that flow S to X1 to Y1 to T in the very beginning, which had value A naught. We take the sum of these values, we get A naught plus summation n equals 1 to infinity, step 1 plus step 2, so an plus 1 plus an plus 2. And this is why we had this weird value over here. We needed this for this recurrence. We needed this recurrence for this sum. So while we originally constructed the counterexample, the authors had the sum in mind. This was the thing on their mind. And then we got all those fancy values. I've written it in a forward fashion, but the thought process was backward. Now an plus 1 plus an plus 2 by the recurrence, like the reason we care about the recurrence, it's just, yeah. So let me take this to this side. So an plus 2 plus an plus 1 is an. That's what I've done here. A naught plus summation n equals 1 to infinity an. So it's just n equals 0 to infinity an. And that is b by definition of b. But as I claim here, we can do at least 4b, right? Okay, when 4b doesn't matter, you can just see this. We can do 2b, s x3 y4t, s x4 y3t. These are all paths without any red edges, so they have capacity b. So we got 2b right away, but clearly this won't let us exceed b at any point. This approaches b. So this algorithm, it doesn't work here. Oh, by the way, it has a name. It has a name. It's pretty famous. It's called the Ford-Fulkerson algorithm. Ford-Fulkerson. Like just type the part whichever you heard clearly, and it will just show up. Okay. So this algorithm is not working for the real numbers, but for the naturals, we are doing fine. And you can take this as an exercise. It's not hard at all. Like it's not even an exercise. Just think about it for 2 seconds. Uh, if I make the capacities rational numbers, you can use the same logic and show that the Ford-Fulkerson algorithm works. Don't think too much about it. Now what we are going to do is We know that this works for naturals. We know that this works for rational values of capacities. Remember that the natural rational thing I'm talking about, those are the capacity value restrictions. And here the things which we are making generally is again the capacity value. So if it works for naturals and if it works for rationals and it suddenly doesn't work for reals in this context, just tell me, wouldn't you think it's weird? And the thing is, you are supposed to feel weird because the thing is, it does hold for reals. It still holds for reals. We just need to optimize things. What do we need to optimize? The thing is, every time you think of an algorithm, something that might come up your mind is it's supposed to be pretty methodical. And here, what you're doing is we are picking any augmenting path we find, literally any. It could be anything at random. So maybe what we can try is we can make a particular kind of choice of augmenting paths. Like maybe if our choice is nice, that's the thing, right? Maybe you're just making bad choices. You have just very bad choices. So if you make some nice choices of the graph, the paths, maybe the algorithm terminates. And the thing is, if you make the right choices, it does terminate. But I'll just tell you what the right choice is because it's the choice is non-trivial. It's simple, but it's still non-trivial. Like you wouldn't be sure why this works. Every time you take a path which has the shortest length in the residual network, you do not necessarily go along the arrows. So you keep updating the flows. You go through the residual network, so like forward and backward arrows and everything, and you take the shortest path there. The shortest in length. Like I don't want like someone can misinterpret it as minimum sum of capacities or something. No, I'm just saying shortest physical length. So like length 3s x2 y2 t is 3 s x2 y4 x4 y3 t. This had 1 2 3 4 5 6 vertices. That's length 6. We don't care about the capacity values. So the claim is this thing always works. Okay, by the way, at this point, I don't think the PDF has any use. I had to show the counter example that thing has worked. Let's just go back to, uh, is it- yeah, there you go. So we have discussed why this thing is an issue. Now we are going to discuss how to resolve it, and the resolution is doing shortest paths, right? So why does this work? Here's the claim. There's two things that's going to happen. Like it's one thing I'll put it in two ways because that's basically it's important to focus on both aspects while you're doing the proof. The minimum length of the path itself, like you're taking paths of minimal length, right? The path of minimal length, the minimal length itself increases. Would I have an example for doing it, right? I should have an example over which we can do the full process, right? Okay, yes, we could just use our good old example. We could just use our good old example. I'll draw it again. Yeah. So this is 10. I'll first draw the edges. We'll rewrite the numbers later. You don't need to remember the numbers. Nobody cares if you remember the numbers. Cool. So this was 10, this was 9, this was 10, this was 8, this was 6, this was 4, this was 2, this was also a 10, this was also a 10. Right. Now we pick the shortest part. Thing is, this will necessarily work. These two are at distance 1. These are distance 1. These two are at distance 2. And this is a distance 3. The shortest path must have length 3 right now. So let's say I'll pick this path. I go 10 to 9. I should number them again, right? I should number them again. So 1, 2, 3, 4, 5, 6. Hmm. So you go 1 to 3, you go 3 to 5, and you go to 5 to 6. So this augments a flow of 9 here. I just write 9 here. This is fine. Now we again want a shortest path, like this vertex is saturated. This edge is saturated. And do remember, we can always go backwards if we need to, as long as you're not, as long as you're not taking this below 0. Do we have another 3 vertex path? You guys are not going to respond anyway. So here's another. Here you have the 10 for 10 paths. Actually, now that I have done distance labels, right? If I'm looking for a distance 3 path, it's always going to be distance, some vertex in distance 1, some vertex in distance 2, then you go to 3. The only way you can go bad is if you went to distance 1, then you went to something distance less than 1 somehow, or distance equal to 1. You need to keep increasing the minimum like the distance they have from here. That thing should keep increasing. So this is another path. Again, you have the restriction of 4 here. So you have 4, 4, 4. Cool. So this is also saturated. Without these, do you see a path of length 3? Yes, there's a path of length 3. It's 1 to 2, 2 to 5, and 5 to 6. This is a path. So now this goes 4 plus 1, 5. You get a 1 here, and you get a 1 here. Right? Okay, so what's the sum now? 9 plus 5, we are at 14. We can do better. So do we have any paths of length 3 left? We have none, right? So we'll go for path of length 4 now. This is capacity 5. So we go 1 to 2. We go 2 to 5. Instead of directly 5 to 6, we do 5 to 4. This is completely unused. Now we go 4 to 6. So you have a capacity of 6 from 4 to 6. 5 to 4 is also capacity 6. 2 to 5 is capacity 7, right? Because you have flow of 1. 1 to 2 is capacity 5. So 5 is a restriction. So we put a 5 plus here, and you put a 5 plus 1 here. This is 5, and this is 5 plus 4, 9. And our total flow value is 19. And now, as you will see, now we have achieved the maximum value. Hmm. This is the maximum, and we will always achieve the maximum here. I don't want to do any more explicit examples. Cool. So we are actually technically speaking, I'm supposed to be there only till 8, and after this I'll get a bit preoccupied, so I can't extend it even if I want to. So we will discuss a brief sketch of why the algorithm works. I'm very sorry about that. I'll detail it in the notes I'll be sending. Like the notes I'm going to send, they'll be very well detailed, and I'll remove all the inaccuracies we had when I was showing the PDF. And it will also come with a bunch of problems, which, as I said, we guys can freely discuss over the Discord. Like, just feel free to ping me and everything, I'll respond. Cool. So, hmm. So what we do is we have the key idea to showing that this always works is like, see, the first thing is like the goal is to show that this algorithm terminates. Once you know that the algorithm terminates, then the maximum min cut thing holds. Okay, just showing that the algorithm terminates is all you want. So what do you mean by terminates? There's a finite number of paths you get. And I have already told you guys why that happens. We see that the path length is increasing. So we discussed two parts. One, why does this never decrease? Two, why does this strictly increase after a while? It could just stay constant, like neither increase nor decrease. Why does it strictly increase after a while? Hmm. So this was the example. And I'll briefly discuss what happens here. So we have the idea of a level graph. What's that? I was labeling these guys with the distances they have from S, right? The shortest possible distance you can have. For example, you can reach one to three from 1 2 3, but I can just directly reach it as one. See, I have an edge here. So 1 2 3 is not my shortest path. 1 3 is, and you can have multiple shortest paths, but you care about the single length these shortest paths have. So it has a distance label of 1. So I'll remove the exact numbers. I'll just put the distance numbers 0, 1, 1, 2, 2, 3. These are the distances. So a level graph is essentially a subgraph where you draw the edges here if and only if these edges are present in the original thing. For example, there's this edge. I'm not going to add this edge because it's not even here to begin with. Then then again you'll only add them if the distance is here. Distance between these two edges they differ by 1. 0 and 1, this differs by 1. In fact, very strictly, if it's pointing towards this vertex, this is supposed to be the one with greater distance. Okay, now we had an edge here from 1 1. We have an edge from 2 2. We will not care about these. I'll draw the ones we'll care about. Cool. So now an important thing to note is as the shortest path you've added will always be a part of this. Why? Why would that be the case? Oh, by the way, these distances are for these distances, the distances are taken over the undirected graph. You could say that uh, I cannot take this path. I cannot take 1 3 2 because 3 2 is a reverse arrow. But no, I'm talking about distances on the undirected graph. That's going to be important. So now the thing is, why must the shortest path you choose here lie on this level graph? The thing is, so let's say your path it goes from a way such that let's consider the closest vertex where this thing differs. Like the closest distance you can go, it differs. What you do is, let's say your path was like this. So this is where you have the difference. You don't increase it by one. So I'm saying from here onwards, your path must get longer. Why? Because as you go in this direction, the furthest you are from the source, this value can only go up by at most one. And why can this only go up by at most one? That's because uh, let's say it went up by at least two. Let's say this had a distance three and this had a distance one, right? So I just take the distance one path to here and then I get a distance two paths to here. So three cannot be the the least distance it has from zero. It cannot be the case. So it cannot be three or four or five or something. So this increment is always at most one, right? And now that the increment, the value here is three, I know there's some path which has length three, right? So I can move by three vertices incrementing every single time. There is some way. And thus, if the path which we have, the shortest path which we have, if it uses any of these edges, then the rule that it has to strictly increase by one, which is what I was talking about all this while here, that gets disobeyed. So first off, your edge is the thing is always here. Now the thing is, once you picked a path, let's say I've used the black too much. Let's say I picked this. This is one of the shortest paths. Now that weights were 10, this was 9, this was 10. I've saturated this, this goes out. Now I delete this. I forgot mentioning this, but our level graph should have unsaturated edges everywhere. Right, so I delete this. And now the thing is, every time you're adding an edge, let's say now you can add not now, but like let's say you had to add this edge at some point. I'm saying it would be a back edge earlier. Back edge as in this distance is either the same or it is decreasing earlier before deleting this edge. That would always be the case. I'm sorry, I'm not going into this too much detail and writing out the proofs properly, but we are well over time. So yeah, that's the thing. And the other thing which again I cannot prove now, I'll just mention it. Like we've discussed the part where the length does not decrease. I'll just quickly tell you about the part where the length must increase. So you're deleting every time you're adding a path, you're deleting vertices here, right? And so you're deleting edges. If you keep deleting edges, this will eventually empty. That should not happen. So what would be happening is sometimes the edges would keep getting added. What you can show is every time you get the chance to add an edge, the maximum distance increases. This is something we'll either discuss on Discord or you guys should figure out. I think I should leave you guys for a day first and think about the lecture regardless of what doubts you get. And then we can start discussing. Anyway, that's the thing. Now what happens is, so before adding an edge, you can have at most mod 8 deletion. We can have at most, the deletion could be number of total edges in your graph. Right, that's an upper bound of the number of edges you can delete without adding any. Right. And after this, let's say the maximum length increases by one. And then you'll have to do that process all over again. So you get another here, and you keep doing this till it reaches a maximum length, like the path reaches a maximum length. Now the thing is, this maximum length is restricted, right? It can be at most v. You cannot have see the thing with paths is, I mean you subconsciously, but if I say it out loud, they cannot repeat vertices. So the maximum length you can have of a path is the number of vertices. So each of these is a bounded sum set, bounded as in mod is a bound for how long it happens before this grows up, right? It could be less. It's not more. That's all we know. So the total number of iterations is less than equal to mod e plus mod e plus mod e plus. This goes on till mod v times at most. Maybe less, but we don't care at most. So you find at most mod v mod e. By the way, this is the number of words and this is the number of edges in case I've been doing a bad job and you guys are so lost that you don't notice this. So this is mod v mod e. This is the maximum number of augmenting paths you could have to calculate before you reach the max floor. So we have shown that there's a finite number of computations to do. Well, not shown really. I've just skimmed over all the hard parts like, quite literally. So yeah. So at this point, I must stop the lecture. It is kind of sad because I was just planning to go over the details and then I thought we could actually discuss a proper example of how to use the maximum midcut theorem. Like I just tell you a fancy theorem, the flows and stuff. Like flows, you don't even know whether they're going to come of any use. So you might want to see some examples to see where how we put it to some use. And I was planning to discuss how you can use to show the Menget theorems in case you guys know what it is. Even if you don't worry about it. I'm going to do stuff pretty detailed in the notes, and we can discuss anytime on Discord. That's fine. I'll always get back to your Discord. Like if not immediately, then eventually. So Abhay, I think it's time we stop. Is that fine?
Yeah, awesome. I'll stop the recording.
Cool.